large-scale application development, particularly in the cloud. And that includes some of the things that I work on from day to day, which is Kubernetes, Docker, things like etcd, and other things as well. So if you have any questions, if you have really burning questions, stick your hand up and I'll do my best to answer them. If not, we'll save them for the end. And I may not be able to answer all of your questions, but I do know a product team that might be able to answer them. So if I can't answer them, I'll get your answer for you. You can tweet me on at TEKGRRL, and it's at the end. It's normally on all my slides, but I'm using this special format today. So let's talk about Golang. And Go is effectively an open source programming language, but one of the key aspects of it is that it's very easy to build reliable software with it. And that's really why we made it, because the goal is, internally at least, and now generally, to make it much easier to build things with applications that can scale to large lines of code, and also to many users and to scale across our entire enterprise, such as Google's. One of the non-goals is really to not basically do more research into programming language development. That's not what it's for. It's not really there to say, hey, look, we build a bigger, better language than you have. And I think some languages are probably a little bit guilty of that. Golang is here purely and simply because we needed something different. And so we decided to build it, not necessarily from scratch. It has many C fundamentals. But we did want to design it to meet our own requirements. And some of those I've removed from here. The kind of things I don't like talking about because they're kind of hubrisy. It's like how many millions of machines we have or how many millions of lines of code we have. We have lots of code and we have lots of machines. And we have lots of things we need to run. We need to run in an efficient and very, very reliable way. Because how many of you have actually been to Google search and found it didn't work? It doesn't happen. Last time I asked that question, somebody put their hand up and said, I use Bing, which is kind of funny. So we need reliable systems. People depend on these systems, and we wouldn't be successful if we didn't have things that people could go to. Batteries. Oh. My voice is going. I really do apologize. I find it really hard to give talks when my voice is going because I'm focusing on my voice and not on my talks, my content. Oh, I can't get it off. Come on. Emergency repairs. It's still working at the moment. You guys can hear me in the back, right? Okay, cool. You won't do in a minute. We're just going to take the batteries out. So, yeah. Long goal is effectively not to break ground in programming language research. And the history, we don't really care about the history too much. It was incepted in 2007. Wow. Yeah, it was incepted. People talked about it. It wasn't actually built and ready in 2007, but that's when we first started talking about it. Lots of interesting and famous people who were involved, and more since. And also, it's been open source since 2009. Very active community. It's language-wise, on GitHub, it has more stars, except for 2 other languages. I'm not quite sure what they are. If you can guess, let me know. The language is pretty much stable. Go 1.0 was released in 2012, and we've had 6 iterations now of product-ready code. So at Google, we use it quite extensively. But we still use other languages. We still use things like Java. We still use things like Python. We still use JavaScript and Clojure and all of those kind of things that we've developed in the past. We still use all of that stuff. But we do have many, many projects that have written in Go purely. Millions of lines of Go code. And some of the examples of public-facing efforts are things like Kubernetes. Kubernetes is a cluster manager, container cluster manager, which we'll talk about shortly. Well, we won't talk about it in detail. That's my other talk. Also, download servers for downloading stuff from for Chrome OS, and for Android, managing all of those dependencies. And also a thing called YouTube Vitess, which is a MySQL balancer. I'm not sure why it's got balancer on there, but it basically allows us to run sharded MySQL in containers. Everybody wants to run everything in containers nowadays, and this is a really great pattern for deploying sharded versions of MySQL, highly scalable, in containers, and Docker containers on Kubernetes, effectively. So basically, the original target was to build network systems with it, large-scale systems with it, but it's become a more general purpose. And I think we have to kind of like pivot a little bit on the way we design it and develop it, because that general purpose use wasn't really probably there on the outset. We didn't probably aim for that initially, but it's getting more and more general now. So who uses it besides Google? So many, many people, and many big names on there, including people like Twitter, who have written extensively about some of the things that they've done with it. Same with Pass.com for Facebook. People like SoundCloud, and also, interestingly, Uber use it as well. So many, many different people use it, and we'll look at how we can actually run Go later as well. So concurrency. Let's talk about concurrency. So this talk really was split into concurrency is not parallelism and concurrency and parallelism, comparing them. I don't want to get into that argument because I know it's kind of religious. How many people think concurrency is parallelism here? Because that's the argument that's been going around for quite a while, and I didn't really want to get into it because it seems to be fairly divisive. So let's just define concurrency on its own without worrying too much about what parallelism is, the ability to actually run things in parallel. Concurrent program becomes kind of like a software model, a development model. Because I think when I first started doing concurrent development just with the standard thread library in Java, like 10 years ago, 12 years ago, it was kind of very hard to reason about things. It was very hard to actually think about what you were doing. And I think what Go is kind of pushing towards is having this, making this an actual model for software development. So that's what we needed. You know, the amount of times I've actually thought of how an IDE would look that would allow and support concurrent application development. Being able to highlight where your code path was based on certain operations. Because code, read sequentially and functionally, doesn't always scan very well because you're never always quite sure what it's doing at any given time, particularly in parallel. So being able to model concurrency is very, very important. It's becoming much more important as well. And the simpler we can make that, the better. So effectively, concurrency becomes a way to structure our software, the way to model our software, and ultimately in a way that supports the development of clean code that interacts very well with the real world, with things that we care about. And concurrent programs can, of course, run on a single processor. We have the scheduler to thank for that. We don't have to kind of block on a thread running on a CPU. We can run concurrent tasks or tasks concurrently on the same single processor. And of course, a well-written, this is kind of sketchy as well, a well-written concurrent program might run efficiently in parallel on a multiprocessor machine. That is not a given, because we all know the complexities of doing this kind of stuff. And I read an article by somebody who works at Docker currently today on concurrency. And he had to apologize because he got it quite wrong. His code was very, very wrong, and he was corrected by somebody else. So it's quite one thing to actually run concurrent applications on a single processor. It's a different thing entirely to run them on a multiprocessor, where race conditions are much more likely to be prevalent. So being able to model concurrency is extremely important, and that's quite important for the Go language, and it has had this right from the start. This hasn't been added on afterwards. This is a core part of the language itself. So ultimately, as a model for software construction, concurrency has to be easy to understand, has to be easy to use, and ultimately it has to be easy to reason about. You know, it has to be that you can look at your code or look at somebody else's code and actually understand what it does. And I don't think that's always going to be the case with code that actually is written on a single screen, goes from top to bottom, without actually having some kind of directives that show that kind of thing being broken off. But I think Go takes one step forward to making it a little bit more readable and a little bit more easy to reason and understand. So, concurrency in Go. Concurrency in Go is really supported by two main concepts. There are other things as well. There are supporting libraries that help us. We're not going to really go into much detail with them today. The first is a Go routine, and the Go routine is like a thread control. It's not an actual OS thread. But it has its own local variables and has its own stack. And we'll go into more details about some of the features of Go routines shortly. These things are very easy to create and they're very cheap to create as well, unlike threads, which are generally much more expensive they have stacks, they come at a cost to actually create, which is why we do a lot of thread pooling in operating systems. And ultimately, we have this thing called a channel that carries typed messages. Everything is typed in Go. It's a statically typed language. And we use the channel to actually pass messages between Go routines. OK, so this is a boring example. And it's not that boring, though. Hopefully, it's not a boring talk, but just a boring example. And some of these examples, of course, are going to be a little bit contrived. So the way we present code in this present thing, we can actually edit this code. We can add additional imports if we want to, and I quite like that. It makes life easy to use, but the one thing I miss from my presentations in Google Docs is that I cannot collaborate easily on these slides. I can't share them with my colleagues and have them comment on them. It's a lot more, well, a lot less collaborative in that way, but it does have some important features, and the ability to edit code live and to run code is extremely important. So this is a Go program. Some of you who are already familiar with Go will know what this does. Most of you will be able to infer what it does anyway because it's fairly straightforward. The syntax is very C-like. We have semicolons. No, we don't. There's no semicolons. But they are there ultimately. They get added by the Alexa at some point. I kind of dislike that because it's like we're hiding these things for no real reason at all. And it's the only thing about Golang that I don't actually like. But we do have curly braces, we have functions, we have imports, we have packages. Everything in Go is in a package, and we can import other packages using the import statements. So it's very easy to do dependency management within Go. And you'll find that once you use it, that it is quite easy to manage those dependencies. There's some really good documentation about the nightmares you have to go through with C. And I think if anybody's done any C or C++ development, you know what it's like to have lots of different includes and lots of different files. So Go ultimately simplifies that. And there are some rules. I'm not going to talk about them today, so I want to get into concurrency. But ultimately here we have a main package. If we want to have an executable, command line executable, we need to have a main package. And we also have to have a main function. This is the entry point for the underlying operating system. So in this case, we have a function called main, and we have another function called boring. And the main function calls boring. So let's run that code and see what happens. You can see you know what it's going to do, right? Can you see that? You guys at the back see it? Yeah, okay. So we know what it's going to do. It's going to iterate, it's going to keep on printing boring, 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 boring. It is pretty boring, right? So that's an example. What we can do is make it slightly less boring. In this case, we just add a variable sleep in there. So we now have a variable between 0 and 1 second sleep time, and that looks a little bit different. Of course, this is pretty straightforward, right? So our duration for our sleep is random now, and we can close that and go on to the next one. We can do that in the background. So it's generally fairly simple to do this kind of thing in most languages. And I'm not familiar with all languages. I'm not familiar with the likes of Scala. I don't develop in Scala. But I know that there are very, very good support for concurrency in many, many different languages nowadays. I'm still back in the old days of Java when you used to have to do thread.run and such like. And concurrent libraries that Java have introduced have made life a lot easier for other people. Python, I've written a lot of code in Python. It's not so easy to do concurrency in Python. But we think Go is pretty easy. And for this, really, to run that method, that function in the background, all we have to do is add this keyword, Go. And that's effectively creating a Go routine. So this will go off and do this on another thread, or at least it will execute it on another thread. It will create the Go routine for us, and something within Go itself will actually schedule that on the operating system. And again, the operating system will schedule that thread for execution at some point. So we're doing this in the background. And you can guess what's going to happen with this one, right? So it's going to fall off the end, and nothing's actually going to happen. Because we entered the main function, we called the boring function on another thread, we didn't block, we fell off the end of the program exited, and so did our Go routine. Okay? So what we could do is maybe do something crazy like this, which is stick a sleep in there so we can actually see something happen. So this is the same code. I'm not showing it all. We have the ability to actually hide some code within the code file that we're including in the presentation. And I've done that here. So basically, we can just see the main method. And the main method, again, it starts off the go routine. We print I'm listening. We sleep for a little while, 2 seconds in this case. And then we print you're boring, I'm leaving. And we can run that. That's all it does. The interesting thing about this, and one thing I can't actually understand currently, and I need to get to the bottom of it, is it always does 5 iterations. And there is no, the count is indefinite. We could loop forever. If I change this for 7 to 3, it will always do 7. And I have no explanation for that currently. So if anybody can think of one, let me know. But I will investigate. It's quite strange. Right, so basically we're cheating a little bit here. We are off doing something on a different thread of execution. We're printing to the screen and we're interleaving what's coming out from the other routine, the Go routine itself, to the screen at the same time. We could do this a little bit differently, and we could use wait groups. And I'm not really going to talk about wait groups. I did this slide earlier just to kind of show how it could be done in a better way. In this case, we use a wait group, and the sync library within Go has a couple of options. One is the ability to run things only once. You may try to run it many times, but you'll only be able to do it once. Or we have a wait group. And now, in this case, we can say, like a condition variable, like we're waiting on a condition variable, we effectively want to count down until all of the threads that are on this wait group have actually completed. And to do this, we basically create our Go routine, we create our wait group as a global variable, we do wg.add to effectively say we're starting the Go routine at this point, and we allow the Go routine to remove itself from the wait group. And it does that using a defer statement. Basically, that means do this at the end when we're finished. So we're saying defer wg.done, so remove ourselves once we've finished executing. So done will effectively remove us from the wait group. And down here, we block on wg.wait, which means we're waiting for all of the threads that are registered with the wait group to finish. All of the Go routines that are registered with the wait group to finish. Sorry. So ultimately, what happens with this one? Something like this. In this case, I'm just printing 10 times. So the actual Go routine in this case would do 10 iterations of the print boring, and we would wait for all 10 to complete. We could do that on 10 separate Go routines if we wanted to, in which case we would just kind of increment that, adding one all at a time to the wait group, and then wait for each Go routine to finish and take that off of the wait group. Okay. So Go routines effectively are very similar to lightweight threads. They are not threads, much more lightweight. They start off with very small stacks and they can be resized as needed. Go programs can potentially have hundreds and thousands of them, and you can get away with that. You can't really get away with that with threads, which may have half a K, 1K, even bigger stacks. And that grows very quickly. And also, to create a Go routine, very simple. You just add the Go keyword, and you pass in a function or maybe a closure, and we'll look at some closures shortly. It's ultimately the Go runtime that schedules these Go routines onto OS threads, and ultimately the scheduler on the operating system that schedules those on the processor. Any blocked Go routines don't use a OS thread, so again, they are very lightweight. Okay? So, going back to our original Go cheating application. Which one? That one? No, that one, yeah. We cheated here. We actually waited. We weren't actually doing these things together. They weren't both cooperating right into the screen. They were doing this independently. So the main thread will be writing I'm listening, and you're boring, I'm leaving, and the Go routine will be writing boring 0, boring 1, etc. So they weren't really collaborating with each other. They weren't communicating with each other in any way. So in order to do real-time communications, actual real communications between Go routines, we need to have some construct. And that construct is the channel. So a channel in Go effectively provides some kind of connectivity between two running Go routines. And that includes the main Go routine as well, because that's running in its own thread. So this effectively allows them to communicate. And declaring and initializing is fairly straightforward. We have two ways to declare variables or initialize variables as well. Within Go, we can either do var c chan int. That means we're creating a channel of ints, and channels are typed. We can't use a channel of int with strings, for example. And then we create the channel itself using this make command. So don't worry about the details behind the make command. This is kind of idiomatic. So just make chan int will create the channel. Or we can do it with the shorter form, which is just c colon equals, not an assignment operator. So it's just a short variable declaration operator. And we can assign that straight to C using inference. In order to send a message on a channel, and again, one here is a literal. We're just sending that to the channel using this send operator. Let's call it a send operator. It's like a crow's foot. So effectively, we're saying, here's the channel, send one onto this channel. And in order to receive from the channel, we have value equals, and then a receive from the C, from the channel. So this is the receive operator. And in this case, we're using slightly different forms. We have white space on the first one. That's not absolutely necessary. You can do it any way you like. It just makes it more readable. And effectively here, we have a much more useful way of actually presenting that. Because we're saying this thing will be assigned to this value, as opposed to making it another part of the operator like equals. It doesn't read so very well if you separate them with white space, but it is possible. So ultimately, we will receive a value from the channel and write it to the value variable. So in order to use channels, and we have some more example code, in this case, we're going to actually tie the Go routine, the function boring, with the main thread. And in order to do this, we create a channel, a channel for strings in this case. And then we call our Go routine with our function. And in this case, we pass in the channel. So we had to have the channel available to both Go routines, the sender and the receiver. So we pass it into the Go routine, and then we effectively iterate, and we receive from the channel. So in the printf statement, format is a package that we use for printing to the terminal or to some kind of output device. So we're receiving from the channel, and in the boring function, we take the channel, and now we continuously send messages to the channel. So again, we're using this operator, and that's sending messages to the channel. So we have the send here, and we have the receive up there. And really, nothing can happen until both of them are ready. Okay, so if the receiver is ready to receive, but there's nothing there, it will block. If the sender is ready to send, but there's nothing to receive, it will block. So either of them can block at that point. Things only will start happening once both of them are ready. So once we have something to send, and when we have something to receive, that's when things will start. So at this point, the main function will drop into the loop. It will stop while it's receiving until something comes along on the channel from the boring Go routine, and we'll move forward. And that will look something like this. And we're using, again, a random duration. So we'll see something similar to what we saw before, but we're now actually, okay, so we only got a count of 5 in the loop here. I don't know why I did that. Didn't need to. So basically, we just counted to 5. We sent 5 messages to the channel, and then we exited the program. All right? Okay, cool. Anything more I want to say about that? No. So let's talk about synchronization. Just go back over that again. So when the main function executes, the receive operator with the channel, it will effectively wait for a value to be sent. And similarly, when the Go routine, the boring function executes, see receive value, it will receive or send value. It will, when the boring function executes, yeah, okay. It waits for the receiver to be ready. So the sender and receiver must both be ready. They must both be able to play their part in the communication, otherwise they're going to stick there. And obviously that's difficult. We can close channels, though, by other means, or even on other Go routines. So ultimately, the channels will communicate and synchronize. Okay? So the next one is a select statement. And the select statement isn't like a standard type of select statement, but some languages that have these. In this case, it has a special purpose, a very special purpose that is for channels only. And in this case, what we're going to do is we're going to have two channels we care about. And whichever one sees some data initially will be the one that we care about. That's the one that will be selected, and then we will exit the select. So in this case, we have a very trivial example where we're saying we receive from N or we sent from B. So what we're going to do is show a better example here because it actually clarifies how they work better than that example. And I meant to change it. But basically, we're going to block in that select statement until one of those channels becomes active. And then that will be the channel we've selected. That's the one we're going to use. We can continuously go back into that select statement over and over again to receive new stuff, and we'll see that shortly. So we're going to use a very trivial example as well, but it's like based on Google search. So how does Google search work? How does Google search work? It's a good question. We asked that in interview questions, and it's quite complicated because it's really, really fast. And most people not really able to articulate how it does it. And the reason is because it's so simple. It's like we're going to show you now. We're going to build it in a few lines of code. This is Google search. Well, it's not. It's fake search. So what does Google search actually do? Given some kind of query, it will return a set of search engine result pages, SERPs, and some ads as well, probably, and maybe some other things that you don't want. Sorry. How do we get these search results? So ultimately, we send a query to a bunch of different backends. So it's not just one backend here, but we're talking to many different backends. And when you look at Google Search, you have images, videos, you have lots of different things there, and books. You can select which one you want to search specifically, but otherwise we'll aggregate across all of the backends that we have. And so basically, we send the same query to the web search, to image search, to YouTube, to maps, news, etc. And then we get all the results together, and we mix them up, and we send them back to the user. Obviously, PageRank is involved as well, and that's extremely important. But how can we implement that in a trivial way? So here's our fake framework. And the code here is fairly straightforward. It's introducing some new concepts. The first one is the idea of a type. We're creating a type called search, which is effectively a function. And the function will take a query string and return a result. Interestingly, haven't gone over this with Go, but we have the name first, and we have the type, and we have the return value at the end. And the return value can be a name value as well, which we'll see shortly. So here, we won't worry about the variable definitions at the top. Well, not yet. We'll first look at the lower part of the code. Here we have a function called fake search, which takes a kind. And the kind would be either web, image, or video in this case. That's the kind of backend we're going to be creating. So this effectively is the implementation of our backend, fake search. And it will return a search object. Or search function, sorry, a search function, which is the one we defined here in the bold. So the function will take a query string and it will return a result. Inside that, we will sleep for some random amount of time, up to 100 milliseconds, and we will return the result, which effectively is a string in this case, and it will say the kind result for query. Okay, so it will say something like web result for Golang, and that's all it does. So we're basically stubbing out the backend. Very, very simple Google backend. So at the top there, we create some variables, and each one of those will be a fake search. So we're going to call fake search, and we're going to get the function back, which is effectively a closure, and that will be assigned to the value. So we have web, image, and video. They'll all be one of these functions that we've returned here. Okay? So very simple test. We haven't implemented a Google function. We'll do that shortly, but that's the representation of the Google backend. And the query parameter is Golang in this case. So that's the query string we're going to pass on to all of our backends. In this case, in the main function, we just do a start. We get the time. We get the results. Then we calculate the elapsed time, print the results, and print elapsed. And that should look something like this. And so now 100 milliseconds maximum each will run for. That's what the random time interval was. So we're going to get back web result for Golang, image result for Golang, video result for Golang. So we're searching all three of our backends with the string Golang. And every time we run that, we will get back a different value for the time elapsed. and that will go up to 300 milliseconds, obviously. If all three of them took the maximum amount of time, and down to some very small value, they all ran very quickly. Okay, so this is the implementation of that Google function we saw on the previous slide. This is a serial version of it. So very simply, we will just in a serial way, we will execute each of the backends and append the results we get back to a slice of results. Which effectively, again, in this case, is a slice of strings because a result in this code is a string. You'll note here that the return parameter, which is here, is named. So it has a name, which means effectively it's like very similar to actually declaring it at the top of the function. So we're basically saying, I want a result slice called results, which we're going to use for all of our results. And then we're going to return that later. So in this case, what we do is we effectively append to that slice the results from each of the backends, okay, one after the other. And then we return. And again, this is a naked return, and that's possible because we named the return value at the top there. So this will ultimately return results. And if we run this, we will see exactly the same as what we saw before. This is the same implementation, the same code. And we'll see high times and low times. What we need to be able to do, though, is do that in parallel. So we have the same function definition here. It takes a query string, returns a slice of results. In this case, we use a channel because we're running everything in a Go routine. So we need to be able to collect the results back from those Go routines, from those running Go routines. And we do that with a channel of results. And in this case, we do a query. We run each of our fake search backends, web query, image query, video query. The query, in this case, is going to be Golang. And we send the results back to the channel, which we pass in, which we haven't passed in because we're doing these as closures. We can actually access C from within the actual main function here, or the Google function there. So each one of those Go routines will run. We'll write its results to the channel. And down here, we know we're going to get 3 results back. We can iterate 3 times, read from the channel 3 times, and append that to the results array, and then return that array. So now, hopefully, it'll be quicker. And with all these things, we probably need a graph to be able to compare the results from one test to another. But I don't have that ability at the moment. I wish I did. But in this case, we should see everything start to skew a little bit lower. We saw some quite large times earlier, 200 milliseconds, okay, and such. So now we're going to run it a few more times and see if it does skew a little bit lower. And so it's looking like everything's running a bit quicker now. Right? All of these things are running in the background. Effectively, we have 300 milliseconds running together. We should never see anything above 100 milliseconds. Okay? So the next thing to do is to limit that a little bit. So let's do a timeout after 80 milliseconds. So in this case, we have the same code, but we've added a select statement, and we've also added this here. So time after 80 milliseconds. So basically, once we've hit this, we will wait 80 milliseconds before creating a channel called timeout. That's not exactly right, sorry. We will create a channel called timeout, then we will write to that channel once the 80 milliseconds have actually elapsed. So we'll be writing to that channel at some point. At the moment, this actual statement here will create the channel. We'll write to it once the timer has finished. And down here, we have the select statement, and we're going to do this 3 times because we have 3 pieces of data going onto the channel. We're going to wait for one of 2 things to happen. Either the case that something will write to C, or we're going to hit the timeout. Okay? So there are 2 options. Either of those can happen. So let's run that and see what does happen. So you see the first one timed out. So that one was over 80 milliseconds. So we can run maximum of 100 milliseconds. That one was over 80 milliseconds. That was the web one. The image and video ones returned within time, and it did it in 82 milliseconds. So because we hit the timeout, it's always going to take 80 milliseconds whenever we do hit the timeout. But sometimes we won't hit the timeout at all. So in that case, we didn't hit the timeout, but we still took 80 milliseconds. So here's an example. We did web, image, and video, all in 49 milliseconds. We run it again, we get a timeout. So in this case, 2. If we run it for long enough, we'll probably get one where all of them time out. And it did work for me earlier, but it's not going to work for me now. But anyway, you can see now we're saying, don't wait longer than 80 milliseconds. And if web's slow, we won't send back web results. If image is slow, we won't send back image results. Okay, so that's one thing. So in order to avoid a timeout, we can go back to doing what Jeff Dean talked about, long tail latency, and having what they call hedged requests, where basically we're hedging our bets on a number of backends that can ultimately serve our content for us, or do whatever we need them to do for us. And by having multiple backends that are identical, we can say, do this for me, and I'll take the quickest one that comes back. Okay, so we send it to 3. One of them comes back in 200 milliseconds, one comes back in 100 milliseconds, one comes back in 50. We only care about the first one that comes back in 50 milliseconds. We can discard the others. That's called hedged requests. So effectively what we're going to do here is the same thing with multiple replicas of our backends. So for this, we're going to create a new function. This is one we're going to ultimately replace our closure with that we had earlier. And this will take a query string and a variable number of replicas. It could be 2, it could be 3. Again, it's a variac declaration or variac variable. We create the channel. And this time, you've probably seen this before on other slides. We actually buffer the channel. So we know we have an X number of replicas. We care about results from them. We don't want to lose them. We don't really care about them going back to our front end, but we don't want to lose them. So we're going to buffer, and we're going to buffer by length replicas. So that's the length of the actual replica slice. And then we're going to create another function, another closure, which is write into the channel that we've created, the channel results. And then we're going to iterate across the number of replicas using this range function that effectively allows us to range across an entire array, or a channel. And I'm not going to get into that today, but it's quite interesting. And ultimately, we're going to run search replica, that function we created earlier, in a Go routine and pass in the iterated value, so the value of I. And then we're going to write one result back. We're only going to return one result. We're not going to return all of them, which is why we have this here. We're able to do this because we only really care about one result. So we're returning that one first result that we get back on the channel. And we can do this here. This is the first iteration of it where we're just using the replicas here. And we'll have a more extended version, which I think I'll skip to straight away, which is this version here, where we replace the Go routine that we had earlier with our first function. In this case, we say this is the query. We have 2 webs. We have 2 images and 2 videos. And we also have a timeout as well. So we're going to try to make everything happen within 80 milliseconds. Because now we have multiple backends, we're increasing our chances of that happening. So now the rest of the code is the same. If we run this now, what we see is the timing doesn't always look much better. But one thing you will notice is we never get any timeouts now. Apart from that one. We get many, many less timeouts now. It's still possible for us to get timeouts, but it's much less likely. And so we're now skewing to lower values here. If we have more and more backends, we dramatically reduce the chances of ever having that timeout. And that's the way we deal with long tail latency. And still, we have no locks, no condition variables, no callbacks. I mean, just think about how much work it would take. And again, I know you guys have amazing languages, so you can probably do something similar to this in your language. But in some of the more standard languages, like C and C++ and Java, it's probably going to be a lot more complicated to build this than it would be within Go. So in summary, we've taken something that was slow, sequential, and failure sensitive to something that's fast, concurrent, replicated, and robust. Let's talk quickly about tools. We finished the concurrency section. Go has some great tools. Go format and Go imports. Some of these things are already integrated into my IDE of choice, which I'm not going to go to, which is Atom. So I use Atom for all of my Go development. And again, we at Google, it doesn't matter so much which ones we use. We have support for many different options within Google. There's also the Go tool as well, the command line tool, and also Go Doc for creating documentation. Good IDE and editor support, which probably a year ago it would have been not so easy to say that. Things like Eclipse, IntelliJ, Emacs, Vim, and all of them have major support for it. We have code completion, code navigation, all of these. There is no official Go IDE, but many different plugins. Also, it's supported by most of the major cloud providers, including Heroku, Google App Engine, Azure, Elastic Beanstalk. So you can run App Engine on those. Indeed, I have my slides actually running on. Oh, I did have them. I don't have a connectivity. I don't have connectivity currently. So, but anyway, I have my slides deployed here. We'll share them with you later. And ultimately, App Engine has a couple of options. It has a rapid, massively scalable sandbox runtime, which has some restrictions on what you can do in terms of the language, but it's also massively scalable. This is what Snapchat run on. And also we have the VM-based runtime, which runs your stuff in Docker containers. This is much more flexible. It supports pretty much any language construct you choose. You can really be completely flexible about what you run on this. But it offers standard auto-scaling. It doesn't have our complicated sandbox auto-scaling functionality. But ultimately, it's going to get better, and we think we're going to ramp it up to a point where it's going to be as good as App Engine, the original App Engine. Also, we have idiomatic client libraries. So we have these in development currently. They support many of the Google Cloud functions currently. But these are basically handcrafted. We normally also automatically generate all of our libraries. So what we're doing with these is we take the automatically generated ones and add stuff on top of them. And this is all handcrafted, all written by hand. But it is idiomatic. Auto-generated libraries are generally not idiomatic at all. And they're very, very low level. So these libraries are an act of love, basically. And large-scale projects that use Go. We have Kubernetes, Docker. I guess you guys are all familiar with Docker, probably. Kubernetes you should check out. etcd, which is used by Kubernetes, is a distributed configuration management tool, something like Zookeeper, if you're more familiar with that. Also something called Vitess, which we mentioned earlier, for sharded MySQL servers in containers. If you want to find out more, you can go to tor.golang.org. There's also a playground in which you can just run all your code online. You can do the presentation stuff if you want to. I can show you how to do that. It's not in my slides. You can go to golang.org wiki to learn. Lots of tutorials there. And the project itself is on golang.org/project. You can also contribute to Go as well on GitHub. So that's it. Thank you so much. Thanks for listening. How many of you are developer advocates? Anybody? Anybody? No? Okay. I need to speak to more developer advocates. I need to ask some questions. So that's me, at TEKGRRL on Twitter. So you can get me if you have any questions, and I'll be happy to answer them. Thank you.
Just a quick question regarding communicating over channels. Is data being copied or shared between the sender and the receiver?
Copied or shared? No.
Well,
So how do you mean? So like you have a copy of it? You have a copy of it within the Go routine. So, and you have ultimately writing it to some variable within the receiver. That's what you can do. So it's effectively copying it, yeah, but
so
not.
It's copied, right?
Well, it's sending it and receiving it. So like if you were sending a message to somebody, that other person will receive it, they can store a copy of it. You don't actually have to make a copy of it. You can actually use that as a gating function. So you're basically waiting on a channel for something to happen. Something writes to that channel, and all you do is block on that call. So as soon as it happens, you carry on. So it doesn't actually have to receive anything from it. So it's not effectively copying it, but it can copy of it. That data will be available on the other end of the channel. Okay?
Okay.
Right, cool.
Any other questions?
Hi.
Hey.
Can you monitor or can you supervise processes, Go routines, as in OTP does for Erlang?
You can, I don't know about OTP.
Can you monitor or supervise your process? What happens if your Go routine crashes or dies?
You can profile it using a profiler. Do you have a way of actually recovering from a crashed thread or crashed lightweight process within Erlang?
Well, you can link and you can monitor and you can supervise your processes. You know, like, that's what it is.
Not that I'm aware of, but maybe I don't know all of the complicated language structures. There may be something there that's available. And certainly it's an open source tool, so people would have probably come across those kind of things and written something similar. But it may be available from somebody else, or just as an open source package on project on GitHub. But I can find out for you if you're interested.
Cool, thanks.
Yeah. All right, cheers.
Any more?
Any more questions? Hey, hello.
Are your channels multiplexed between Go routines?
Are they multiplexed between Go routines? You
One
can.
channel can be read by many.
Yes.
Or written
You can
by
fan
many.
in. You can do both fan in and fan out on them.
Fan out.
Yeah, on both of them. I don't have any examples of it. Although for the concurrency talk that I actually took some of my first slides from, which is by Rob Pike. It's on YouTube, and he does go into fan in and fan out on channels in that talk. But I just don't have time. I really wanted to show the example at the end. Yeah. No.
Thank you very much.
Thank you. Thanks for the question. All right, guys. If you have any questions in the meantime, just tweet me. TEKGRRL. I wish I'd never used that because nobody ever remembers it. It should be memorable, right? It's not. TEKGRRL. So just tweet me. I'll do my best to answer your questions. If not, I'll find somebody in the product team who can. Thank you very much. Cheers.